Okay, today's goal is for us to be able to understand how to predict whether something is spontaneous or not. That is the ultimate goal of thermodynamics. We have hit the mountaintop today. Yeah, record timing. So I first remind you that spontaneous means the process occurs without outside intervention. It doesn't have to be fast. It doesn't have to be pretty. It just has to go on its own. I think I've said a couple of times over the years, sorry, I do have some typos that I will be fixing as we go. I said a couple of times over the years that generally things tend to go toward lower energy. Normally, that's what we think of spontaneous. Think for a minute of the processes that you know that are exothermic versus endothermic. A candle burning. Once it's on fire, spontaneous, exothermic, boom, done. Lab. Most of the stuff we encounter in lab is exothermic. Most dissolving processes, etc. Endothermic, not so good. Baking a cake. Yeah, you can let it sit as long as you want on the counter. It will not spontaneously bake until you give it some energy. So just by the very nature of us having to put energy in to make endothermic happen, it is less likely to be spontaneous. However, melting ice is an endothermic process, and it is spontaneous. Well, at room temperature it is, but in the freezer it is not. Uh-oh. All right. I said the other day, I think, well, maybe I didn't say it, but things naturally go toward higher entropy. Think about my front table, my favorite example, because it gives me an excuse to have a messy table until next week. Your bedroom, does it ever spontaneously clean itself? Well, maybe if you have a parent doing that for you, but that doesn't count. How about a jar of M&Ms where you have poured in all the blue M&Ms and then all the yellow M&Ms, so it's nice and organized in 2 layers. You shake it. Shake, 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 and they're all mixed up. Higher entropy. Will you ever shake it, shake, 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 and have it happen where all of the blue ones are in 1 layer and all of the yellow ones are in another layer? Yeah, there's a statistical possibility, but it is really not likely to happen. Okay, so generally things go to higher entropy. Yeah, you may have noticed the word generally, which usually causes problems for us. We do have something called the second law of thermodynamics that helps us out with this. And this is on the handout I gave you yesterday. It says the entropy of the universe is always increasing. For any spontaneous process, delta S of the universe is positive. That means increasing. This is why we worked on that yesterday with the signs and whether that means increasing or decreasing. Uh-oh. We did not talk about the entire universe yesterday. We talked about very isolated examples, and the ones we did out of the book, like melting, increase or decrease in entropy. We looked at some chemical reactions. We looked at systems. And now I'm throwing out there the universe. We start to get sad. Fair warning, we're going to get sadder, and then we'll get very happy, all within 30 minutes. I love it. Okay, entropy of the universe. Entropy of the universe, and remember the delta is changed, so change in entropy of the universe equals the change in entropy of your system, what we looked at yesterday, plus the change in entropy of the surroundings. So if we're talking about the universe, we're looking at a chemical reaction there and everything else there. We mastered this one yesterday. You guys did a great job. We did that. Oh. Yeah, the surroundings are a little bit of a problem. Actually, this is the other typo, in more ways than one. Actually, delta H is connected to the entropy of the surroundings. Took space to write. Exothermic. Anything that is exothermic has a delta H that is sign negative. Anything that is exothermic involves whatever our system is, which I will box off, and the surroundings. Exothermic processes involve heat energy being released from the system to the surroundings. So the surroundings are getting hotter. The surroundings are, like, especially immediately around the reaction, not like on the moon, because it's kind of far away. They're heating up. What does that mean for the motion of the particles? More motion. What does that mean for entropy? Increases. So for an exothermic reaction, delta H is negative, and that implies that delta S of the delta S of the surroundings. I can do this. It's positive. Increases. Using the same thought process, we can analyze endothermic. Endothermic delta H is positive. Energy goes into the system. Coming from the surroundings. In other words, the surroundings are losing energy. They are getting colder. Motion is decreasing. Entropy is decreasing. Aha! Okay, this is going pretty good now. We're getting the connections. Yes. You with me? Okay. Now, actually, we need to also consider temperature. Because temperature is going to affect which one is more important to consider, the delta H or the delta S. Oh no. Here's the example for this. Delta H. Let's look at a endothermic. And I go back to the ice cube melting. That's an endothermic process. The heat is leaving your hand, going into the ice cube to convert it from a solid to a liquid. That is spontaneous at low temperatures. So we can have an endothermic that's spontaneous, but there's a connection with the temperature. I'm sorry, it's spontaneous at high temperatures. Melting, melting, spontaneous at high temperatures. If we consider freezing water, exothermic, it's the opposite process. This will be spontaneous at lower temperatures because water will spontaneously freeze if it's cold enough. So we see that delta H and spontaneity, you can get both endothermic and exothermic processes to be spontaneous, but you might have to manipulate the temperature a little bit. And I know you're gonna be sad if I remind you of this, but it's okay. Remember in equilibrium with Chatelier's principle, when we dealt with endothermic and exothermic, and we said, what will force the system to shift one way or another with temperature changes? So remember, exothermic, heat's released. If we want to drive the reaction to go further, shift the equilibrium position to the right, we need to remove heat, we need to cool it. Spontaneous at lower temperatures. Endothermic, heat is on the reactant side. If we want to force the equilibrium to the right, which would be making the process go, if we heat it up and provide more heat, it will be, the equilibrium position will go to the right, and that will be spontaneous at higher temperatures. Oh, this is not so bad. However, it's a little messy. It is a little messy. So we look at the change in enthalpy and the change in entropy, and what if one says it's spontaneous and the other one says it isn't? How are we going to deal with that? We have to take into account the universe and the system and the surroundings and the temperature, and please, someone just help us. We're at the mountaintop. Because someone did come along, and it's someone named Gibbs, not NCIS Gibbs. Although, really, every time I say Gibbs, I imagine that, a head slap. Ow. Yeah. So we have this equation. I wrote it over here in standard states. Given your textbook and a reaction, you can calculate all three of these using Appendix 4. Delta G is the change in Gibbs free energy. It is usually given to you in Appendix 4 in kilojoules per mole. When you multiply by the coefficient, you get rid of the per mole part. So we're usually dealing with this in kilojoules. Easy enough to convert to joules with that. Delta H. Well, that's the one we know it's associated with the reaction. It is the change in enthalpy. The units in Appendix 4 are usually kilojoules per mole. So again, we're dealing with kilojoules there. Delta S, change in entropy. This is of the system. We no longer have to worry about the surroundings because Gibbs took care of that for us. Makes our life much easier. So this is the system. In Appendix 4, the units are joule per mole Kelvin. Once you multiply it by the coefficients in the reaction, you get joules per Kelvin, which tells us that the temperature must be in Kelvin. A little piece of advice, if you are plugging numbers into this, notice joules and kilojoules, make them match before you do the combining. Now today, we will not have time to do a calculation with this, but we're going to keep talking about the concepts. And I can take care of the calculations easy enough after today. I'm going to leave this up there for a little while, and eventually I'll just stop the recording momentarily because it's a lot of words. That equation is a way of connecting all of these changes between energy and entropy. That page, I don't know if you saw it, I had on the top, the devil is in the details, and it got messy. Okay, this equation just puts it all together. It allows us to focus on just one term, that is delta G, to determine spontaneity. Oh, sorry. And when delta G is negative, meaning less than 0, that means we have a spontaneous reaction. I have that on the next page as well. But that way we don't have to worry about H and S and T. It gives us a way to account for the temperature dependence of some of these processes. And I simply point out to you on page 800, table 17.5 summarizes using that equation to predict spontaneity, not with numbers, but just with signs. And we will have time for one example of that at the end of class. And I'll pause the recording for a minute to give myself a break. Okay, so to summarize, if we know delta S of the universe, if that is positive, then we know the process is spontaneous. Usually we don't know that, but every now and then we might be given it. We can look at delta G. If delta G is negative, then we know the process is spontaneous. This is the one we're going to focus on 99.9% of the time. You can still think in terms of lower energy. It's just Gibbs energy now. So we're going to cover a couple of questions that are conceptual in nature as opposed to numerical. So if delta G for something is positive, what does this imply? It is not spontaneous. Let's say like A going to B. If A going to B is not spontaneous, B going to A is spontaneous. So the reverse is spontaneous. If I were taking today's class a different route, we would start talking equilibrium. When initially to get to equilibrium, you have to go in the reverse direction, like you start with all products. That would relate to this. Okay, if delta G is 0, what does that imply? It could go either, so the forward is not spontaneous, the reverse is not spontaneous. There might be a nice healthy balance. It is at equilibrium. And if your brain's going about 42 miles an hour right now, you're starting to make that connection between delta G and equilibrium. So everything naturally goes to equilibrium. And if delta G is negative, we have a spontaneous process until it changes to the point where it's at 0, and then we're at equilibrium. That's it for that page. All right. This is 3 separate questions. We are not thinking G right now. We're just applying all the concepts. So one at a time. Here we go. One at a time. We go like this. Boom. Based on your knowledge, if we go from 2 oxygen atoms in the gas phase to an O2 molecule in the gas phase, will that be an endothermic process or an exothermic process based on your understanding of what's happening there? I can draw it for you. I can do this if you want. Just a second. I always have to think really hard. So I'm going to give you a strategy. If you have a question like this and you're not sure, try thinking about the reverse and see if that one reveals itself to you. Going from an O2 molecule to individual atoms. Yes. So When we break bonds, that's always going to be endothermic, because you've got these two atoms bonded together and you have to convince them to break apart. So it always takes energy to break bonds, and therefore to make bonds, it's going to be exothermic. Okay, new question. For this process, does the entropy increase or decrease? And I mean the system, nothing fancy with surroundings here. Decrease. We go from two gas particles to one. So entropy decreases. So up here, delta H is negative, delta S is negative. If I were to ask you right now if this is spontaneous, you would say, well, according to number one, it looks like it should be. According to number two, it looks like it will not be. So then we have to decide, will this be spontaneous at lower temperatures or at higher temperatures? Turns out it's going to be at lower temperatures, and because of it being exothermic, again, I'm going to go right back to equilibrium and Le Chatelier's principle. If this is exothermic, and we want to drive the reaction that way, we can do that by removing heat. Put ice around the whole thing. That means you're lowering the temperature. Watch this. I get so excited. This is so fun. Now we're going to use that. And I said at the end of class we would do one example. We got 4 minutes, so that's it. We got 4 minutes. One example to show you that chart on page 800, how you can analyze based on signs alone whether something is going to be spontaneous always, spontaneous never, or at high or low temperatures. So we're looking for spontaneous. So we want that, delta G, to be negative. That's our goal. Given this one up here, delta H is negative, up there, minus, okay, I'll do that. T is Kelvin, so it's always positive. Delta S right up here is negative. So we have a negative minus a negative. We want it to end up to be negative overall. Which term has to be bigger? The first term there or the second term there? The first term. This one needs to be bigger mathematically in order to keep the whole thing negative overall. That means the one on the right needs to be smaller. How do we get it to be smaller? We need a smaller temperature. So this is spontaneous only at low temperatures. Yeah, that was 1 minute. We got 3 minutes to spare. I don't know what to do. Do we fill the time or do we stop? Okay, we can stop.